In my discussion of phase transitions so far, we have thus only covered the idealization of gases, with ideal gases being the primary component of what we were discussing. In this next kind of set of videos here, I want to discuss non-ideal gases and some other mathematical models that chemical engineers and chemists have constructed over the history of the study of this sort of procedure in order to kind of better understand maybe gases that don't fit as nicely into the ideal gas category. So I think the best distinction to make initially is what is, or what was, kind of our definition of ideal gases. Ideal gases were kind of, they were the idea that there is no attraction between molecules. Right. So in our non-ideal gases, and water is going to be our primary example, there is attraction between these molecules. So we have to kind of construct some other coefficients or some other variables in order to resemble this characteristic of these gases. So the first equation that is perhaps pertinent to this discussion is what is known as the van der Waals equation of state. And it looks something like this. You're going to see me abbreviate van der Waals VDW a lot in this video, and you're going to see me abbreviate equation of state a lot. Oops, I spelled state there, as EOS. There we are. So what it looks like is as follows. A pressure for a substance of a gas is going to be shown by RT over, this is going to be specific volume here, so this is volume per mole, minus a new coefficient, B, that we haven't talked about before, minus, and this is the entirely new section, we haven't seen this at all, A over V squared. Now, A is going to represent some sort of average attraction between the molecules in our substance, and B is going to represent the actual space that our molecules are taking up, hence its subtraction from a specific volume. So, with those two new constants kind of defined for us here, I think it's time to start looking at what this will kind of do for us in a more applicatory sense. And I think the best thing to do now is to kind of show a phase diagram, but instead of being pressure versus temperature this time, it will instead be pressure versus volume, or PV diagram. You'll hear this referred to as sometimes. Now, for a PV diagram, we are going to be plotting multiple isotherms. What that means is that the temperature will be held constant for these different graphs. Therefore, the only thing changing in perhaps these containers is the pressure and the volume, and they'll have that inverse relationship, which means the temperature has to be held constant. So there's no sort of insulation in this system. And here are what the isotherms are going to look like. I'm going to draw just 3 here. This is kind of a poor man's theoretical drawing of what we would assume these isotherms to be. Now, I'm going to go ahead and define a couple things about these isotherms. For the top one, I'm going to say that the temperature is greater than the critical temperature for the substance. I'll define the critical temperature a little bit more fleshed out in just a moment. For the orange one, this temperature is equal to the critical temperature, and for the green one, this temperature is less than the critical temperature. Now, we're going to talk a lot more about the green one in my next video, in which we'll go a little bit more into the Maxwell equal area construction, and we'll add a couple more coefficients to our van der Waals equation. But for now, we are just going to talk about the orange isotherm, or the one where the temperature is held constant at the critical temperature. So what is the critical temperature / the critical point for a substance? Critical point is one specific combination of volume, pressure, and temperature, in which the substance will kind of exhibit some sort of superfluid state. Let me explain that a little bit further. If I have a container, let's say, of some substance, I'm just going to use water in this example again. So here it exhibits itself as a liquid, and here it exhibits itself as a gas. There's a very clear interphase line, we can say, right here. This is the interphase of the substance. If I were to move this container to its critical point by increasing its pressure and temperature accordingly, and perhaps changing its volume if that is necessary, then what will begin to happen is this line will kind of start to dissolve. What I mean by that is you will no longer be able to see the differentiation between the gaseous and the liquid phases for the substance. Therefore, when we can't any longer see the gas or the liquid phases, we begin to call this a superfluid, is the terminology for that. Now you may wonder, why is the critical point so relevant to our discussion of the van der Waals equation of state? Now, what's really nice about the critical point here is that its graph looks a little special compared to the other two. On its graph, we can denote a specific position right here that would actually be the critical point for the substance. So here would be the critical volume, and here would be, about here, I believe, would be the critical pressure. Now, looking at that point and using our knowledge of calculus, we can kind of determine two things. We would understand that the first derivative of pressure with respect to volume would be equal to 0, as the tangent line to this graph is equal to 0. Similarly, the second derivative of pressure with respect to volume is also equal to 0 because it occurs at an inflection point among this graph. That is a really interesting observation that van der Waals made and kind of talked about in his Nobel Prize lecture. So from this observation, we can theoretically derive some expressions to observe our coefficients A and B. Let's go ahead and do that right now. So we know we're talking about the critical point, so I'm going to be denoting my pressure, my temperature, and my volume as critical with that little subscript C there. I'm just going to go ahead and write the van der Waals equation for the critical volume, the critical temperature, and the critical pressure. So as you can see, this should not be squared. This should be squared. Yeah, I didn't make that squared up there. Good. So as you can see, we are now at the critical point for this substance. And what our observations were is that the first derivative of pressure with respect to volume at the critical temperature is equal to 0. And so let's go ahead and derive this here. We are derivating with respect to volume, and so we need to go ahead and do that derivation here. So RTC will remain a constant. VC minus B will get squared. That will become negative, and this will become positive, and I believe we should get that if I differentiated correctly. So that's our first derivative, and again that we said was equal to 0. So let's do that again and find the second derivative. So let's differentiate again at the critical temperature. And we should have 2 RTC over our specific critical volume minus our B term there, cubed, plus this should be 6A, actually this should become minus now, because we're multiplying by a negative 3, over VC to the 4th, and that is also equal to 0. Now, from the observation that these are equal to 0, we can rewrite both of our derivative equations there. We'll go ahead and write the first one like this by moving over this term to the other side of the equation. And for our second derivative, we will do something similar, this time moving the 6A over our volume to the 4th power to the other side. There we go. Now, realizing all of these are equal, we can go ahead and multiply our two equations by the inverses of each other. Let me explain that a little bit better. So, I'm going to take the inverse of the second derivative equation. Fortunately, it looks like my second camera angle may be blocking that out a little bit, so I'm going to scoot that over. There we go. Take the inverse of the second equation, or the second derivative equation, and then multiply that by our first equation here. And when we go ahead and multiply that over, we will see quite a few terms are going to go ahead and cancel out very quickly for us. For example, our R, our TCs, our gas constants, and our temperatures are going to cancel out immediately, as well as our A terms are going to be very quick to cancel. Similarly, this term will cancel completely, and this term will be brought down to the first power, and this term will also cancel completely, and this will be brought down to the first power. So when I rewrite that, after all of the cancellations, we should have something that looks like VC minus B over 2 here. It's going to be equal to VC over 3. Let's go ahead and cross multiply. And now go ahead and solve for B. So I'll move this over. And now we have found a nice term for B in terms of solely the critical volume. Now, this does make intuitive sense, as I did say, if you remember back to earlier, that B is indeed some sort of measurement based on the volume that the actual gas molecules occupy. So, therefore, this equation for B makes good sense. Now, if I'm to plug this component, or this term for B, back into one of our other equations, we can very quickly find a nice term for A in terms of the substance's critical components as well. So let's go ahead and do that. I'm actually just going to plug that back into the first derivatives equation. So let me go ahead and copy down this equation here for the first derivative. And now let's just plug in our new term for VC over 3 being equal to B. Let's go ahead and start doing some of the math here. VC minus VC over 3 is going to be 2/3 VC. Square that, and this will be on top here. When that is squared, it should come out to 4/9 VC squared. Remember, this is still equal to 0 here, I should note. Let's go ahead and move that to the other side of the equation. And then again, let's go ahead and cross multiply. So 2 times 4/9 is going to be 8/9 VC squared A over VC cubed. Oops, we're cross multiplying. There we are. And then go ahead and divide both sides by 9/8, or sorry, 8/9 VC squared. And then we will find a term for A as being equal to, this is an A, not a 9. This is A, is going to be equal to 9/8 times the critical volume times the gas constant times our critical temperature. So there is our term for A, and let me go ahead and copy down our term that we went ahead and derived for B. Alright. That wasn't too bad at all, now was it? Now that we've derived terms for A and B, I think we can go ahead and introduce kind of another variable here, although this is widely used as a means of calculating the compressibility factor for a substance. So the compressibility factor is we're going to denote that as Z, the compressibility factor. And let's go ahead and define that as Z being equal to PV over RT. Now, we know that for an ideal gas, we have already defined the compressibility factor as 1. This is for an ideal gas. However, using our new terms for A and B, we can now go ahead and solve for this ratio for any actual substance at its critical point. Hence why the critical point is so relevant to us. So let's go ahead and do that. We're basically going to write our van der Waals equation of state, except this time we are going to substitute in our A and B terms here. So let's go ahead and do this. Our critical pressure is equal to gas constant times temperature. Oops. And our A term was 9/8. So, a couple cancellations and manipulations are going to pop out to us immediately. Alright. Then, if I go ahead and multiply this right-hand side here by 2/3 over 2/3, or 1 virtually, to get like fractions, this will be 2/3 times 9/8 RTC, 2/3 VC. It's going to actually determine to be a very easy thing to subtract here. So let's go ahead and do it. 2 times 9 is, let's do this. Let's actually simplify this fraction real quick first. 18 over 24. 18 over 24 is going to be the same as, well, if I divide both sides by 2, it would be 9 over 12. Divide by both sides by 6, that would be 3 over 4. So 3/4 RTC Alright, so then subtract it over 1/4 RTC, 2/3 VC equals PC, and then if I simplify all of that, I will go ahead and find that PC times VC over RTC is going to be equal to 3/8, I believe. And that is a pretty amazing connection, because it means that for any substance at its critical point, its compressibility factor will be equal to 3/8 no matter the substance. So this was a pretty amazing discovery here to relate all non-ideal gases. Alright, so we've gone ahead and done that and derived a term for our compressibility factor. At this point, I think we can actually go on and let's code out and plot some isotherms based on our expressions for A and B for a non-ideal gas substance. Let's go ahead and actually plot it out, and we'll go ahead and plot our models here. So I'll go ahead and I'll put this guy off to the side so that we can still reference him, because it would be so horrible to forget all of our equations. Alright, pin that to the front, over here. Alright, let's go ahead and code this out. What we want to go ahead and do here is we want to plot some isotherms for water, let's say from 275 Kelvin to 900 Kelvin at 25 temperature increments. Let's go ahead and make PV diagrams for those based on these equation of state terms that we've gone ahead and derived here. So to do that in Python, I'm of course going to import my NumPy, and we need to import some sort of plotting function if we're going to plot them. So I like plotly.subplots. That should be a from import make subplots. Okay, nice. And I probably spelled something. Nope, shouldn't be parentheses there, should there? Alright, so that's going to run as slowly as possible, it looks like. So let's go ahead and define our function, our van der Waals function here. And it's going to return our pressure based on inputs of volume and temperature. That import seems to be taking quite a while. Okay, so we said we want it to return, basically this is just going to be our van der Waals equation. So we need to do gas constant times temperature divided by volume minus our B term. Let's go ahead and put that in parentheses. Okay, and then we'll subtract that from our A term over our specific volume squared here. Remember, this is specific volume. Alright, so what do we need to go ahead and define here? We need to define some sort of R term. Oop. Okay. Some sort of R term, which is going to be 8.314. That's just our gas constant. We need to define our, what other terms do we need? We need our B and our A term. Well, we already derived equations for those, right? Let's see. There we go. There's our equations for our A and our B term. So let's go ahead and code those out here. We said A is going to be equal to 9/8 times VC times R times TC. Alright, well, then we're going to need to define our, thank you Siri, we're going to need to go ahead and define, goodness gracious, our critical temperature and our critical volume for whatever substance we have. And let's go ahead and define our B term as well as being the critical volume over 3. So we're done with that now. We need to find the critical temperature and critical volume for water. So let's go ahead and look that up, because I don't have that memorized. Critical volume of water, sure. So here's the critical volume of water. And we said this is in meters cubed per kilogram. And we also need the critical temperature. It should be quite high. It's 374 degrees Celsius, and we can go ahead and convert that to, yes, we can go ahead and convert that to Kelvin by our simple addition problem there. There we are. Awesome. Now, Have we defined everything? I believe we have. Let's go ahead and run that cell. Perfect. Now, we need some sort of volume range to generate our PV diagrams here. I'm just going to do some sort of log space, let's say from log 10 of some extremely small number, that works, to let's do a negative number there. Okay, perfect. So that's going to be our log space. Yeah, that looks about right. So some super small number to some pretty decently large number. Okay, and let's get 1,000 terms. Who cares? Lots of volumes for our volume diagram here. So let's go ahead and plot it. We're going to make subplots. We need our plot there. Amazing. Okay, so let's see. What do we need to do here? We need to find some sort of temperature to plot this with. So for T in range, actually let's do an NP air range function here. So we said we want to do it for water from 275 to 900, let's step 25 kelvins. Wonderful. So for that, each thing, we need to go ahead and do, Python requires colons, we need to go ahead and add to our plot. What are we going to be adding here? We are going to be adding our x values being our volume, remember we said this is PV, and then our y values are going to be equal to, well, our van der Waals function, inputs of volume, and our temperature, which we have defined now. And mode, we can make that lines. Let's go ahead and actually name each one as well. We will name them as functions of whatever temperature we're at, and then they will be in degrees Kelvin. So that works. Now, if we were to plot this out right now, we would get some strange graph. So let's go ahead and actually label, not label, x-axes. We need to go ahead and change the parameters for our x and y axes based on the fact that they will give some extremely low numbers and not really give us the range of values that we're looking to seek here. So let's go ahead and make the x-axis a log. That looks good. And then update the y-axis. We'll go ahead and do that as a different range. This is a range I've already looked at. I believe it's 1e to the -7th, 1e to the 8th. Okay. And finally, we just need to update the layout. Let's see, we'll make the width 800 and the height 600 here. And let's go ahead and see what this looks like. This needs to be type scatter. That's what it's going to yell at me for. I know, I threw a lot into you, buddy. Come on through for me. Let's actually just copy this down and see if I can run it in this cell here. Perfect. So we'll just not look at that one. Alright, and let's look at our plot. And hopefully this will come up at some point soon. Well. Alright. Cool, so this didn't run because it is garbage. So let's go ahead and run this plot cell here. We just want to see what it looks like. and it is running slowly but surely. And as soon as it comes up, we should have a very nice plot here for us to look at. And here is the plot we went ahead and came up with here. So, as you can see, this isn't the plot that we intended. Oh, here's the error in the code. This should be 1.01 times the factor b there. So if we go ahead and run that again, there we are. That's going to look a lot more close to what we were looking for. However, it is still not perfect, as you can see. And this plot isn't as precise in our curves as we want it, likely due to our calculation of the critical volume. Let's see. If we were to try this by idealizing the critical volume, I believe we would come up with a much more precise graph here. Yes, there we go. Okay, so if I were to zoom in on this component here, and we look at this graph, knowing that the critical temperature is somewhere in the 600 and something-ish range. Let's see. Then we would see that our critical point would fall in the range of somewhere around here-ish, which is exactly where our critical point should be. It's about 647, so it should be somewhere around here, which lines up pretty well with our graph. So, I think that's a pretty good start onto non-ideal gases, and in the next video, we'll go ahead and talk a little bit more about what happens when the temperature is less than the critical temperature. Thanks.